So, last class I am explaining about the sampling. Now, I want to explain about how it is quantized. So, as I explained in the last class that there is you have heard about the 24-bit ADC, 16-bit ADC. What is that? 32-bit ADC, 8-bit ADC, talk about the telephone channel signal. So, in telephone channel signal, what is the sampling frequency? 8 kilohertz. What is the encoding bit size? They said 8 bit. So, what is encoding bit size? So, 8 kilohertz means in a 1 second I get 8K sample. 8 kilohertz means in 1 second I get 8K sample. So, if I recorded an analog signal for 1 second, I will get 0 to 8K minus 1 sample. 8 kilo minus 1. So, I can say 8000 minus 1 sample. So, in 1 second 8K sample. Now, each of the sample, is there a sample? Sample means evidence of the signal at that time. So, if I have a sine wave and if I take the evidence in 0th time, the evidence is 0. Let us say after t time evidence is here, after t2 time evidence is here, t3 time in here, t4 time it is again 0. Then I take the evidence in here, 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 let us say here, like that. So, I have the evidence. So, I have an amplitude of the sine wave is A to minus A, or let us say 5 volt to minus 5 volt. So, what is the peak to peak voltage? 10 volt. Negative peak to positive peak is 10 volt. Now, the samples which are time evidence in a particular time will be varies between 0 to plus 5 and 0 to minus 5. Okay. So, now I have to discretize this y axis. So, when I say the sample, if I say this is 2 volt, that is continuous. So, it is a continuous valued, but it is discrete in time. Now, I have to discretize this value. So, how do I discretize it? Nothing but a quantization. What is quantization? So, what I say, this 10 volt space can be divided into certain step. Let us say, so I have a sine wave, here is my sine wave, this is the time instant. Sorry, so this is the time instant, I have taken this time instant, this is the time instant, okay, this is the time instant. So, these circles are the time instant I have taken. So, I have a signal which varies from this level to this level. Let us say I divided the whole level in a number of 1, 2, 3, 4, 5, 6, 7, 8. So, I divided my peak to peak amplitude in 8 level. 1, 2, 3, 4, 5, 6, 7, 8 level. Okay or not? So, that means if my sample value is in here, I will assign the level of the sample value maybe in here, if it is above 50%. So, suppose, so this is a step size, I can say called step size. So, this is the step and again this is the 8th step. So, if the sample value in between 2 steps, what is that means? So, this is my step size. Now, I have a signal. Now, suppose I have collected the sample in here. So, this sample either I can assign to this step size or I can assign to this step size. If I assign to this step size, then I can say it is the below, the error will be positive. If they assign in here, error is positive, and if they assign in here, error is negative. So, somehow I get an error, that is called quantization error. So, before I come into the quantization error, I come in again. Let us say what is this 8 bit is said and what is this 16 bit is meant for. So, let us say I have a signal, then I take the sample, evidence here, 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 again here, 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 here. So, that is the time sampling. So, my signal now I get a sample in here, here, here and here again, here, here, here and here. Now, I say that I want to represent each of the sample in let us say 2 bit, let us say instead of 8 bit 2 bit. So, each sample has to be represented by 2 bit. So, how many possible number is how many decimal number is possible in a 2 bit, how many variations are there? Bit can be 0 0, 0 1, 1 0, 1 1. So, this is 0, this is 1, this is 2, this is 3. So, I can say that whole voltage negative and positive can be divided in a 4 step. So, I take a 4 step. So, this is the 1, 2, 3, 4. So, I divided the signal in a 4 step. Now, if my samples are within this step, I will assign this value. So, this is positive 1. If my sample is within this step, I assign this value. So, this will be let us say this is 0, this is minus 1, plus 1. So, I can say that way. So, that step I assign. Similarly, when I say I have an 8 bit representation, how many step size is possible? 2 to the power 8, okay or not? 2 to the power 8, but 1 bit will be the sign bit. So, if I take the peak to peak value, then I know that peak to peak value can be divided into 2 to the power 8 step size. So, what should be the width of the each step size? So, I have a let us say it is a minus 5 volt, it is plus 5 volt. So, what is the total dynamic range? The total range is 10 volt. How many division is possible? I said 2 to the power 8 division. So, each of the division corresponding to this delta volt. So, this delta volt equal to 10 volt divided by 2 to the power 8. Now, if I say since the signal has a negative and positive both, it has a negative and positive. So, sign also is important. So, 2 to the power 8 means 1 bit for sign. So, 2 to the power 7 is the variation. So, I can get 256. So, 2 to the power 8 is 256. So, I can say 0 to 127 and 0 to minus 127. The value of the sample will be 0 to 127 and 0 to minus 1, minus 2, minus 127. Is it clear? So, this is called quantization. So, I am dividing the whole sample space in a step. So, that step, each steps depends on the how many bits I have encoded each of the sample. Let us say this one. So, max minus min. So, what is max? Max is plus 5 volt minus plus 5 volt divided by L. L is the zone. So, I can say let us say the quantization level is delta, then I say Q quantization level is equal to X max minus min divided by 2 to the power n. That is the delta value. Okay or not? That is the delta value. Step size. Now, what is the quantization error? Now, you see, I have a step size here and here. Now, a signal is like this. So, I can say if the signal is above 50% of this level, so suppose this level is 0.5 and this level is 1. Now, I say my signal is 0.7. So, I want to find out the difference, this level. So, signal is above 0.5, 0.7 in here. What is the difference? 0.2. Okay or not? So, now I said if it is 50%, so what is the step size? Is 0.5. What is the 50%? 0.25. So, if it is 0.75, I should assign 1. If it is below 0.75, I should assign 0.5. Then what is the error? When I assign 5, my error is 0.2. When I assign, if it is, let us say 0.8, then I assign here, then also my error is 0.2. So, what is the minimum error? What is the maximum error? Whenever I said this is the original signal, so error is original minus assign. So, original is 0.7, assign is 0.5, so error is 0.2. Original, or I can say assign is 0.5 minus assign, original is 0.7, so assign minus original. So, I can say it is minus 0.2. So, whatever you can take. So, I can say that it somehow it is nothing but a maximum error and positive and negative both sides, either q by 2. So, it is minus q by 2 to plus q by 2. If I say this one, I take the original minus assign error. Similarly, original is 0.7 and my assign is 1. If it is, let us say 0.8. So, 0.8 assign is 1 is equal to minus 0.2. So, somehow it will be only half. So, that is why the quantization error is q by 2 to q by 2. What is q? Q is nothing but a step size. What is the step size? Is the maximum swing of the voltage divided by number of steps. Okay. So, 8-bit quantization 2 to the power 8, 16-bit quantization 2 to the power 16. So, if I increase the bit, the value of the q will be decreased. If I increase the q, if I increase the n, 16-bit, so more precisely I can, the step size will be very low. So, quantization error, that is half of the step size, that also very low. So, if I increase the bit size, the quantization error will be minimum. If I decrease the bit size, the quantization error will be maximum. So, 8-bit, let us say 8-bit, 16-bit, 24-bit. Which one is high error? 8-bit. But think about, suppose I sample the signal at 8 kilohertz sampling frequency and each sample is encoded with 8-bit, then how much memory is required to store that digital signal? 8 kilohertz multiply by 8-bit. So, I can say 8 into 1, 8k into 1 byte. So, I can say 8 kilobyte. If I represent each sample by 24-bit, then my memory size will be 8 into 3, 24 kilobyte. So, when I increase the resolution in the vertical axis, that I mean reduce the error in the quantization error, my memory requirement is also increases. So, when I say 24-bit, that means, so suppose I want to transfer a signal from this point to this point without any compression. So, if I want to transfer a 8-bit signal, this is 8k, so bit rate is 8 kilobyte per second is required. But when I want to transfer 8K sampling frequency, but 24 bit is my encoding, then I require 24 kilobyte per second. Similarly, image. When I talk about the image, what is an image? I come to the, okay, first I complete the sampling frequency, then I come to the image. So, now I said encoding bit. Now, suppose I want to increase the sampling frequency. So, instead of 8 kilohertz, if I sample at 16 kilohertz, then in 1 second, if it is 8 bit encoding, I require 16 kilobyte per second memory or transfer rate. Now, if it is 24, then 16 into 3, 48 kilobyte per second I have to transfer. So, either if I increase the sampling frequency, then also the bit rate required is high or memory requirement will be increased. If I increase the quantization, then also, but in both the cases the error will be minimum. Because if I want to, what do you mean by increased sampling frequency? That means time axis I get a more resolution, more closely to the analog signal. When I say increasing encoding bit, that means y axis, that the value axis, I have a more resolution. So, I get the more accuracy. If you see, if you buy a audio cassette, audio CD, if you see its sampling frequency is 44.1 kilohertz and bit rate I think it is 24 bit per second per sample. Encoding bit size is 24 bit. That is why only 3 to 4 songs are there in a one CD, because it is uncompressed version, original audio CD. Now, when you go for the MP3, that is a compressed version, that is different issues. So, understand. So, now I just, if I give you first I give you a one dimensional signal example and then I come to the two dimensional signal example. Let us say one example I have given. An audio signal is recorded using following format. To a 50 millisecond signal in PCM WAV format, how much memory is required? PCM WAV format means it is stored sample by sample without any compression. So, what is the sampling frequency? 8 kilohertz. What is the encoding? Each sample is 2 byte. What I have to store? I have to store 50 millisecond signal. How much memory is required? So, 50 millisecond signal, how many sample will be there? In 1 second, I have 8K sample. So, in 50 millisecond, how many samples will be there? 8 into 10 to the power 3 divided by 10 to the power 3 into 50. I converted this second into millisecond, or you can convert it second into millisecond into second. So, I can, if I both way you can do. So, I can say 400 sample. So, I have to store 400 sample. So, each sample is 2 byte. So, how many bytes is required? 400 into 2 is equal to 800 byte. Is it clear? If I say same thing, I want to record 2 second signal. So, in 2 seconds, how many sample will be there? In 1 second, 8K sample. In 2 seconds, 16K sample. Each sample 2 byte. So, 16 into 2, 32 kilobyte memory I required. Understand? Now, other way. Let us say if the above signal fundamental frequency is 200 hertz, how many sample will be there in one period? Fundamental frequency is 200 hertz. How many sample will be there in one period? So, what is the T0? Is nothing but a 1 by 200 second. See, in 1 by 200 second, how many sample will be there? In 1 second, I have an 8K sample. So, in 1 by 200 second, how many samples will be there? Very simple. So, those are the sampling, byte, bit, all conversion. You can accustom with that things. Then I talk to an image, no. So, let us say talk about that image. When you digitize an image, what is an image? Image is a spatial, so I have an x axis, I have an y axis. I have an image like this. So, what is digitization of an image? It is nothing but a pixel. So, I have divided the x axis. So, I draw the x axis and then I divided the y axis. Both axes I have sampled, and then it create an x y coordinate. Pixel shape is not rectangular. We do not know the pixel. Pixel shape is, let us say, a circle or whatever, but there is a coordinate system of the pixel, x and y, x and y, and the intensity of that pixel, that so the I is a function of x and y. Okay. So, how many sample I will say? The sampling frequency of the x axis and sampling frequency of the y axis. So, that is why you call 400 by cross 400 image. So, 400 pixel by 400 pixel image. So, x axis there is a 400 pixel and y axis there is a 400 pixel. Okay. So, that is an image. So, I is an x and y. Then there is a quantization. What is quantization? I is quantized. I can be represented by a 8 bit, it can be represented by a 3 8 bit. If it is a color image, you say the true color, that is nothing but a 8 bit for R, 8 bit for J, green, and 8 bit for blue. Understand? So, 8 bit, 1 byte required for R information, 1 byte required for G information, 1 byte required for blue information. 24, 3 into 8, 24 bit. So, I is quantized using 24 bit. Let us see the black and white image. I is quantized into 8 bit. So, 0 means let us say black and 2 to the power 8 means pure white. So, in between there will be a grey. Understand? So, that way even now when I say the video is a continuous signal. When you look at it is a continuous, appearance is a continuous signal, but if you see it exactly in time axis, the all still image which is called frame. So, more than 25 frame per second if I play, then I said it is continuous due to the perception of vision of the human being. So, that is why if you see when you buy a television or when you see the video specification, it is written HD, 60p, 30p or 30i. So, those are the specification standard. 30 frame P means progressive, 30 progressive frame per second. So, that is another technology, progressive and inter alias. So, number of frame per second is the sampling of the time axis. Understand? So, that way you can say that everywhere it is digitization, and only when you say talk about the digitization, you have to think what is the time instant I have taken and how I have divided the y axis. So, quantization bit and sampling things, those are the important issue. Now, if I told you another problem, let us say I told you that I want to record, I have recorded a speech signal with a 16 kilohertz sampling frequency. 16 kilohertz sampling frequency with a 16-bit encoding. Now I said I want to process only 20 millisecond of the signal. So how many sample will be there in 20 milliseconds? How many sample will be there in 20 milliseconds? So in 1 second I have a 16K sample. So 16 into 20. So I get sample. So sampling to memory, memory to sampling, sampling to time, time to sampling. So those conversion you have to do. And another issue I have said in analog the frequency is called radian per second, but in digital it is radian per sample. So which is called normalized discrete frequency. Normalized discrete frequency. So what is normalized discrete frequency? Omega is nothing but a radian per second divided by Fs. Radian per sample. So suppose I told you write a C code or generate a 2 kilohertz sine wave with a sampling frequency 4 kilohertz. Let us say I told you to write a program, C program for generate a sine wave signal whose sampling frequency is 4 kilohertz and the frequency of the signal is 2 kilohertz. So I said the frequency of the signal F1 is 2 kilohertz and Fs is equal to 4 kilohertz, let us say, or let us say 5 kilohertz. And I told you to write a C function or write a program to generate 4K sample, 4000 sample of this sine wave using the sine function in computer. So how do you do it? So I know in sine theta I know how to write the sine omega t. So I know the sine, what is omega here? Capital omega 2 pi f. So 2 pi into 2 kilohertz. So I can say sine 2 pi into 2 kilohertz, 2 into 10 to the power 3 into t. This is the time domain. Now I have to do in digital domain. So I can write a for loop for I equal to 0 to 4000 or n equal to 0 to 4000. I will write sine 2 pi into 2 into 10 to the power 3 at what interval? 1 by Fs divided by 5 kilohertz, 5 into 10 to the power 3 into n. So this is omega divided by Fs. This cancel. So I can write down only for a simplified version is sine 4 pi n divided by 5, and n varies from 0 to let us say 4000. So I collect 4000 sample whose sampling frequency is 5 kilohertz and the signal is 2 kilohertz signal. If you plot in Excel in some or MATLAB, you can see the sine wave. The sine wave in computer is a digital because it is not continuous. So I have to define the sampling frequency. So if I increase the sampling frequency, so if I decrease the sampling frequency, t will be increases. So decrease sampling frequency means this t. When I increase, t will be less. So as I increase it, the point will be more closer, so time resolution will be more closer. Understand? Now if I told you, write a program to generate a composite XXN which has a two frequency component or two monotone. One is 500 hertz, another is 2.5 kilohertz and sampled with 10 kilohertz. Collect, let us say you have to collect first 1000 sample of Xn. So, two frequency component 500 hertz, 2.5 kilohertz. Now, I come to the another problem. Suppose I said that instead of 5 kilohertz, the Fs is equal to let us say 3 kilohertz. Then I told you what should be the, if I converted the digital signal to analog signal, what should be the new signal? I said I have an analog to digital conversion. I apply a sine wave whose frequency is 2 kilohertz. Then I sampling frequency is Fs is equal to 3 kilohertz. So, which is less than twice B. So, it is twice B is 4 kilohertz. Then I said I have applied a DAC, sampling frequency is 3 kilohertz. What should be the output signal Yn if I apply Xn in here? You think on it. What should be the Yn? So, what new kind of signal I will get instead of 2 kilohertz sine wave, what kilohertz sine wave I will get? So, next class we will discuss about that and I will pictorially I will show you that how this aliasing effect in here in case of a sine, taking an example of sine wave and cosine wave. Okay? Thank you.